Hi, this is Mrs. Rodriguez with experimental and theoretical probability. So let's go ahead and look at our warm-up first. The warm-up says a bag contains 9 red marbles, 3 blue marbles, 3 green marbles, and 3 yellow marbles. Determine whether each statement correctly describes the likelihood of an event. Select true or false for each statement. So statement number 1 says the probability that a yellow marble is selected is 0. So what we need to remember is that in statistics, probability is ranked from 0 to 1. 0 being impossible. Okay? And 1 being 100% certain. Okay? So the probability that yellow marble is selected is 0 means they're asking, is it true or false that getting a yellow marble is impossible? So, is it impossible? No. And that's because even though there are nine red marbles, 3 blue and 3 green, you also have these 3 yellow. Are the chances of getting a yellow marble high? No, but there's still a chance it could happen. So this would be false. It is not impossible. It's definitely possible. Okay, second statement. The probability that a red marble is selected is 1. So remember, if 0 is impossible, 1 is 100% certain. So the question's asking, are you 100 or is it true or false that getting a red marble is 100% certain if you were to reach into that bag and grab a marble? And once again, this is false. Why? Because yes, we have the 9 marbles, but we have blue marbles and green marbles and yellow marbles, not just the red ones. So while there's a good chance you'll get red because most of the marbles are red, you could still maybe get a blue, green, or yellow. So that would be false. All right, last but not least, the probability of selecting a blue marble, green marble, or yellow marble are equal. So first we need to see how many of each we have. So let's go ahead. I'm going to change this to green. We have 3 blue, 3 green, and 3 yellow. The important part to know is that each of them have the same number. And if they have the same number, then yes, it's true. They have an equal ability of getting chosen from the bag. So that is true because they have the same number of each. All right, so today's lesson is about experimental and theoretical probability. So first we're going to start with experimental probability. Experimental probability is the ratio, which, by the way, means it's going to be a fraction. Let's not forget that. The ratio of the number of times an event occurs to the total number of trials. And it is what does happen, and I'll explain what that means in a minute. Theoretical probability is the probability of an event happening based on the possible outcomes. It's what should happen. Okay, so theoretical and experimental. Experimental is what does happen. Theoretical is what should happen. So what do we mean? Now, I know you can't see it, but I actually have a quarter. And if you look at a quarter, it has 2 sides. And mathematically, we know that if I want to know the probability, and let's use the shorthand. The probability of getting heads, if I flip that quarter, is 1 out of 2 because there's 2 sides and only one of the sides has heads on it. So that's theoretical probability. What should happen? This one is based on the math, okay? Based on the math, that's what should happen. It should be 1 out of 2 or 50% of the time if I flip this quarter, I should get heads. Now, experimental probability is different because it's when you actually flip the coin and see what happens. So theoretical probability is, yeah, based on the math, this is what should happen, but that's just our best guess, right? Our best educated guess, or tool we can use to see what we think is going to happen, okay? But in reality, experimental probability is what actually happens when we flip the coin. So I'm going to go ahead, and I know you can't see, but I'm going to keep a tally of heads on one side and tails. I'm going to flip it 10 times, and I'm going to see, I'm going to flip it. Let's do 10 times and see how many times I get heads and how many times I get tails. So let's go ahead and flip. So I flip once, I got heads. Heads again. Heads again. Heads again. Oh, wow. Tails. Tails. Heads. That's 1, 2, 3, 4, 5, 6, 7. Okay, 3 more flips. Heads. Tails. Heads. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so I just flipped the quarter 10 times, and look at what happened. I ended up with heads 1, 2, 3, 4, 5, 6, 7 times, and I ended up with tails 3 times. So if I was doing what actually happened, experimental probability of how many times I got heads, it would be 7 times, and I flipped it 10 times. So it'd be 7 out of 10 times I got heads. And if you were to calculate the percentage of 7 over 10, it would not equal 50. You would get 0.7, which, if you remember, that means you move the decimal over 2 places, and you end up with 70%. So notice, even though theoretical probability says I have a 50-50 chance of flipping a quarter and getting heads, when I actually flipped the quarter 10 times, I actually ended up getting 70% of the time getting heads. So that's the difference between theoretical and experimental. Theoretical is what should happen based on math. It's our best guess. Experimental probability is, okay, what actually happened? What results did you get when you did the experiment? Okay, so moving on. Number 1, use the spinner below to answer the questions. Then spin the spinner 10 times and complete the table below. So A, what is the theoretical probability of spinning a section with stripes? So remember, the first thing we need to do is count how many outcomes we have. So 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. So I already know that my total number of outcomes goes on the bottom. So now we see what is it looking for, and they want to know stripes. So out of the 8 sections, only one of them is stripes. So that means 1 out of 8. Okay, and if I go ahead and divide 1 by 8, that's going to give me 0.125. And remember, the decimal moves over 2 places, and we end up with 12.5%. B, what is the theoretical probability of spinning a section with stars? Okay, so I'm going to erase this, and now I'm looking for stars. So there's stars here, and here, and that's all the stars we have. So out of the 8 total possibilities, 2 of them have stars, which we could simplify to 1/4, because remember, if both numbers are even, that means 2 goes into them. And we always have to simplify our fractions. So 1 divided by 4 gives us 0.25. Remember, we move that decimal over 2 places to make it into a percent, and we get 25% probability of getting stars. All right. For C, what is the theoretical probability of not spinning a solid or striped section? Okay, so the important part is they want not solid and not striped. So, not solid. Well, this one's solid, this one's solid, 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 and not striped. This one is striped. So what do we have left? Out of the 8, we have 3 left. Okay, 3/8 cannot be simplified, so we just leave it alone. We're going to divide 3 by 8, and we get 0.375. We can move that decimal over 2 places, and we end up with 37.5% probability of not getting a solid or a stripe. Okay, so now with this same spinner, we're supposed to calculate what happens, or we're supposed to keep track of what happens if we spin the spinner 10 times. Now, in class, students were given the opportunity. You got a spinner. I gave you guys a copy of this spinner with a paper clip so you could spin it 10 times and see what happens. Unfortunately, over the video, I can't show you that, but what I can do is I can spin it on my end and then show you the results I get, and you can see how it works. And then if you want to do a spinner at home, you can. All right? Or you can just use my data to answer the questions. So let's go ahead and spin the spinner. So I ended up with, my first go around, I ended up with a stripe. Second spin, stripe again. Oh, wow. Third spin, stars. Fourth spin, white again. Or I'm sorry, not stripe. I got white. Fifth spin, white again. Sixth spin, stripe. Seventh spin, stars. Eighth spin, stars. 9 spin, stars. And the 10th spin. Oh wow, I got stars again. Okay, so that's a tally mark. A tally mark is when you just kind of quickly put a line to show how many, to keep track of how many times you get something, okay? So now it says total number of spins. So for stripes, we got 3. I'm just counting them. For white, I got 2. For dots, I got 0. And for stars, I got 5. So out of the 10 spins, that's what happened. Now, for experimental probability, remember it's a fraction, and it's going to be the total number of spins on the bottom, and then how many of each one we got on top. So out of 10 spins, 3 of them were stripes. Out of 2 spins, or I'm sorry, out of 10 spins, 2 of them were white. Out of 10 spins, 0 of them were dots. And out of 10 spins, 5 of them were stars. Okay, and then I can calculate the percentages by dividing the top dog by the bottom number. So 3 divided by 10 is 0.3, which gives us 30%. Remember, moving that decimal over 2 places. 2 divided by 10 is 0.2, which gives us 20%. 0 divided by 10, well, 0 times that happened, that's just 0%. And 5 out of 10, we would simplify that to 1/2, which we know is 50%. Okay? So if you notice in part A up here, what is the theoretical probability of spinning stripes? It's supposed to be 12.5%. But down here, when we actually did it, the experiment, we actually got 30%. And in the second part B, what is the theoretical probability of spinning stars? It said 25%, but when we actually did it, it came out to 50%. So notice that the theoretical and the experimental don't match up. And in reality, you would have to do the experiment a lot for it to match up with the theoretical. So what do I mean? 10 is not enough times to do the experiment to have it equal what theoretical would equal. You need to do an experiment minimum of at least 100 times and then you start getting really good data of what's supposed to happen. So the more experiments you do, the closer it will get to matching the theoretical probability. So when we only spun the spinner 10 times, notice the percentages are way different than the theoretical. But if we were to do this, let's say 100 times, the numbers would be much closer. We might not get a perfect 12.5% for stripes, but it'll be around 12 something, or maybe like 13.1, right? It starts getting closer and closer to that 12.5. And we might not get 25% exactly for the stars, but it'll be pretty darn close, like 24 or 24.9 or 25 point something. But the more experimental probability you do, the closer that number will get to the theoretical probability. So number 2 says, are there any results in which the theoretical and experimental probability are the same? Why or why not? And so the answer to that is no. Oops, I need my pencil. So no, they are not the same, because we did not do enough trials. Remember, you got to do a minimum of at least 100. But in reality, if you wanted to get extremely good data, I would say the thousands, but at least 100. So 10 wasn't enough trials. We would need to do a lot more than just 10 spins to get a good idea of the data. All right, relative frequency. Relative frequency is, let me go ahead and change colors. Relative frequency is the total number of successful attempts divided by the total number of trials. It can be used to make predictions. As the number of trials increases, the relative frequency of an event will approach the theoretical probability. So what does this mean? That means that relative frequency is when you go from the fraction part of experimental probability. So let's see, this section here, this is your experimental probability, the fraction, the ratio, 3 out of 10, 2 out of 10, 0 out of 10, 5 out of 10. But the relative frequency is what happens when you divide it and you get those percentages. So this here is actually your relative frequency. These percentages here, this is your relative frequency, which we've already been calculating. Okay, and the more of them you do, see right here, as the number of trials increases, the relative frequency in an event will approach or get closer to the theoretical. So the more experiments you do, the closer that our percentages for relative frequency will become close to what they're supposed to be for the theoretical probability, which is what we just discussed, right? The more experiments you do, at least 100, will get you closer and closer to those percentages you expect, like getting heads on a quarter being 50% chance. If you only flip the quarter 10 times, it's not going to be 50%. I mean, it could be, but probably not. You would have to flip it at least 100 times, if not more, to really get heads to be 50% and tails to be 50%. So relative frequency, we go from experimental probabilities fraction and we turn it into a percent. All right, so the spinner at the right is spun 50 times and the results are shown in the table below. Complete the experiment below. So we have here the results and we spun 15 times. So for the number 1, they had 12. So that's going to be 12 out of 50, right? For the number 2, it's 8 out of 50. 3 is 13 out of 50. 4 is 10 out of 50. And 5 was 7 times out of 50. But we want the relative frequency, so we want the percentages. So 12 divided by 50 is going to equal 0.24 or 24%. Actually, let me do that in a different color. So 0.24 or 24%. Okay, so 8 divided by 50 is 0.16 or 16%. 13 over 50, that's going to be 0.26 or 26%. 10 over 50 is going to be equal to 0.2 or 20%. And 7 over 50 is going to equal 0.14 or 14%. Okay, so that's a relative frequency. Remember, you're taking what actually happened in the experiment, that fraction or ratio, how many times it happened over the total number of experiments, and then you're going to divide it and get that decimal and percent. All right, so then it says they want us to complete the experiment below. So here we have spin it 100 times and calculate the relative frequency. So everyone in class was given a copy of this spinner and a paper clip to use as a spinner on it to spin it 100 times and calculate it. At home, you could do the same thing. You could draw the spinner and print it off my Google Classroom, a copy of the spinner, and do your own experiment 100 times. I'm not going to do that here, but remember, once you spin it 100 times, keep track of what you got, how many you got for each number, and you're going to write that here. And then for relative frequency, you're going to write it as a fraction, right? So for every fraction, it's going to have 100 on the bottom because you're going to spin it 100 times. And then you're going to divide it and get your relative frequency, that percentage. So on top of this fraction is going to be how many times. For the first one, it's going to be how many times you got the number 1. For the second one, it's going to be how many times you got the number 2. Then the third one's going to be how many times you got the number 3. Fourth one, how many times you got 4. And then the fifth one, how many times you got 5 when you spun it that 100 time. Okay. Word of advice, if you want to do this quickly, have one person spin it 100 times while somebody else quickly jots down the results, so that way it can go faster. If you're having to spin yourself and jot it down, it might take a little longer. Okay, and then you're going to go ahead and finish number 3, and then through 6, and then we're on to the next part. So then it says experimental and theoretical probability. Read and answer each of the questions below. Use the number bank to help you check your solutions. Not all numbers will be used. All right, so number 1, in the media cabinet at Jacqueline's house, there are, let's get our highlighters, 7 comedies, 4 mysteries, and 4 documentary DVDs. What is the probability of randomly selecting a mystery DVD from the cabinet? So first, we need to know how many total DVDs we have. So we have 7 comedy plus 4 mystery, that's going to be 11, plus 4 documentaries. So 15 total DVDs. Okay, so then the probability of getting, right, the probability of getting a mystery DVD is going to be, well, if there's 4 mysteries, be 4 out of 15. Okay, so that is our answer, 4 out of 15. We can't simplify it. 4's even, 15's odd, and they don't have a factor in common. So you're going to go through, and 2 through 6 are just like number 1. You're just going to go through, read the problem, and then try to write out what the probability of each one is. Go ahead, and I want you to pause the video, try to do that on your own, and then when you're ready to check your answers, restart the video and see if you got them right. Go ahead and pause the video now. Welcome back. So let's take a look at these. Number 2, Mrs. Mitchell's coin purse has 20 coins. There are 6 pennies, 4 quarters, and 3 dimes, and the remainder are nickels. What is the theoretical probability of selecting a nickel? So notice they don't give you the number of how many nickels, but we can figure it out because we know there's 20 coins altogether. So if there's 20 coins altogether and 6 are pennies, we can take out 6. 4 quarters, so we can take out 4 quarters, and 3 are dimes. We can take out 3 dimes. So this was our pennies, quarters, and dimes. We don't need those because they only want to know about nickels. That means there are 7 nickels in the coin purse. There are 20 total coins. So the answer is going to be 7 over 20. Okay. Number 3. The spinner below is spun 10 times. If the experimental probability of landing on 3 is 1/2, okay, then what is the difference between the experimental and the theoretical probability? So they landed on 3 half the time, okay, and they want to know the difference. So first of all, we need to remember what difference means, and difference means to subtract. So they want us to subtract the experimental, or I'm sorry, the theoretical probability from the experimental. So they got 1/2. So 1/2 of so 1/2 is what they got for the experimental. So we're going to have 1/2. But we look and it's 1, 2, 3 possible outcomes. So the theoretical probability, okay, the theoretical probability is actually 1/3 of getting C. So it's going to be the theoretical minus the experimental. So here's the theoretical here, and this is the experimental here. And we're supposed to subtract. Now, if you'll remember, when you subtract fractions, you have to have a common denominator, and here we don't. The first one has a 3 on the bottom, and the other one has a 2, so we got to make them the same. So I got to think, what number does both 3 and 2 go into? And I'm going to say 6. So that's 3 times 2 and 1 times 2. And then to make 6 for 2, it would be times 3. Whatever you do to the bottom, you have to do to the top. And we end up with 2 over 6 minus 3 over 6. Okay, so now we're going to subtract them. And actually, I wrote these backwards. So we actually want them the other way. So this is going to end up being 3 over 6 minus 2 over 6. The experimental minus the theoretical. Sorry. And 3 minus 2 is 1. We leave the bottom alone, and you end up with 1 over 6 as your answer. Okay? All right, for the next problem, it says the following cards are used in a game. If each of the cards is turned over and shuffled, then how many of the greater chance is there in drawing a spade over drawing a 7? Okay, so first we have to see how many spades we have. So I'm going to make spades green. So this is a spade, spade, and spade. Okay. The other thing we're looking for is a 7, and I only have the 1 7. Okay, there is 1, 2, 3, 4, 5, 6 possibilities. So that means, okay, now remember, it's the experimental minus the theoretical. So for the experimental, oh, no, I'm sorry. We're just doing what's the chances. So in this case, what's the greater chance in drawing a spade? Well, over a 7. Well, the 7 would be 1 out of 6, right? And the spade would be 3 out of 6. Uh-oh. I'm all over the place. Hold on. Okay, so the difference between drawing a spade over drawing a 7. So there are 3 spades out of the 6, and minus how many times you can get a 7, which is 1 out of 6. So 3 minus 1 is 2. We get 2 over 6, which we can simplify because both numbers are even, so 2 goes into both of them, 1/3. So our answer is 1/3. Sorry, I had classroom and try to ask me a question, so I was a little distracted. All right, number 5. A fair coin is tossed in the air 4 times. A fair coin, okay, this means that it has a heads on one side and tails on the other. There's no tricks to it. There's no heads on both sides or tails on both sides. It's Head on one side, tail on the other. It's tossed in the air 4 times. If the experimental probability of landing on the tails is 1/4, then what is the difference, there's that word again, between the experimental and theoretical probability? So remember, difference means to subtract. And in this case, we're subtracting, once again, the experimental from the theoretical. So experimental minus the theoretical. Okay? So, or actually, no, I'm sorry. It's going to be the theoretical. Well, let me show you what's going to happen. So the experimental is 1/4. We know that a coin has 2 sides. Okay, a coin has 2 sides, so that's the total outcomes on the bottom. One of the sides is heads, the other side is tails. So there's only 1 tail on the coin. So we know the theoretical probability is 1/2. The experimental is 1/4. So they want to know the difference. They want us to subtract them. So what I'm going to do is, we need a common denominator. So I know that 2 goes into 4. So I need to change the theoretical so that the bottom is a 4. So I know 2 times 2 is 4. Whatever you do to the bottom, you have to do to the top, and I end up with 2/4. So I could do experimental minus theoretical. You'd end up with a negative. It wouldn't really make sense. So it should be theoretical minus experimental, and we get 2/4 minus 1/4, and you end up with 1/4. Okay? That's the difference between the experimental and the theoretical probability based on their experiment. All right, number 6. During a team building game, participants reached into a bag and randomly selected a colored flag, which determines their team. Go ahead and get a color running. If there are 7 green, 5 red, and 3 yellow, what's the theoretical probability of selecting a red flag? So in this case, the first thing we need to do is calculate the total number of outcomes, right? Because it's the number of successes over the total number of outcomes. So altogether, how many flags are there? So there's 7 plus 5, which gives us 12, plus 3, which gives us 15. So there were 7 green, 5 red, and 3 yellow. That's where I got my numbers from. So there's 15 total flags. We know that the probability of getting red is going to equal how many red over the total number. So there are 5 red flags, so it's going to be 5 over the total, which is, my pen's not working, which is 15 total. So it's going to be 5 over 15. Now, I know 5 goes into 15, so I can definitely simplify this. I can divide both by 5, and I get 1/3. So the probability of getting a red flag is going to be 1/3. Okay, so if you got those all correct, go ahead and give yourself a pat on the back. Now, moving on. The next part's going to be your spiral homework number 2. Remember, there's a problem from each section that we've either learned in the past or are currently learning. So the first one is select the expression equivalent. Number 2 is scale factor. Number 3 is your probability question. Number 4, what's the decimal equivalent? And number 5, proportional relationships. So go ahead and do those on your own. Remember, I have posted the answer key on my Google webpage, so you can check to see if you did them right or wrong and know if you need to ask me any questions about them when you come to school tomorrow. And as always, if you need help, if you have questions, if you're confused on something, you just need to speak with me. Whatever the case may be, you can always ask me during class. after class or make an appointment to see me during office hours. Hope you have a great day. Bye.